All right, hi folks. Another in a series, and this is for the few people that missed out on Tuesday's presentation. We're moving to randomized experiments. We had already talked a little bit about the basics for experiments, the terminology like factors and levels and treatments and that kind of thing. So we had a little organizer to help us kind of put things together. And so now we're going to move into a few other topics along with our first experimental design. So this is actually a bunch of review. We've already looked at the control as being the first principle of statistical design of experiments. And so we're just trying to beat the effects of confounding variables so that we can attribute all of what we see in an experiment to our treatment. So we're going to control sources of variation other than the factors. Remember, factors are explanatory. They're what we impose into the experiment. Other than the factors we're testing, by making conditions as similar as possible for all treatment groups. So we're going to see in a minute our first experimental design. It's going to involve rats. And there'll be two groups of them, and other than what the experiment is about, they'll be living in the same room with the same lighting and the same amount of water and the same temperature and the same day that their cages get cleaned, and everything else will be the same except for the treatment. So that's what we want. We're going to beat back those confounding variables so we can try to establish some causation, and that's the whole point. All right, so we will be comparing two or more treatments or by choosing a control group. You'll see how that comes together. All right, so a control group. This, I'm afraid I may have left this to be a little bit confusing, but it's just a group in experiment having a treatment that shouldn't have an effect but creates a baseline for comparison. If you already have a group that's present, that's named something else that's doing that, all right, that is your control group. It may not be named control group, but that's serving as the control you need for your experiment. So if you already have it, two groups, one serves as a control, one as a treatment group, don't add an extra group called control. Because the only thing you can do, like if it's for, old kind of feed, new kind of feed, and then no feed at all, that doesn't make any sense. So we did touch on this on Friday. This is the second principle of statistical design of experiments, randomization. Before I even put anything up, just picture this. All right, you've got 40 individuals, and the experiment is to try out a new kind of running shoe to see if it increases running speed. So you're going to put 20 people in with the old shoes and 20 people in with the new shoes, randomly assigned. But let's just say that you have 9 runners out of those 40 that just happen to be like crazy fast. Do you want them all together in one group? You know what I'm saying? I mean, wouldn't that introduce a systematic kind of bias into things? Okay, so if you are able to randomize those, 9 people into the two groups, you can cancel out or nullify that systematic characteristic that they're bringing into the experiment. So, comparison effects is only valid if treatments are applied to similar groups of experimental units. All right, they don't have to be identical. They can never be identical, but if you can make them similar, then whatever characteristics they bring into the experiment can't be confounding because they're equally spread in both directions, right? So randomization will make groups approximately similar. If you do get all the runners or systematic differences among groups in a comparative experiment, if all those runners show up in one group, you get a possible source of bias. So our remedy is to impose chance to make group assignments. And hopefully we won't see all 9 of those crazy fast people in one group. I suppose randomly they could show up there, but the chances are pretty small. All right, so we have control, we have randomization, we have replication. Okay, all right, the issue here is twofold. There are actually two things we need to concern ourselves with. And the first one is going to be a replication of each treatment on many units. All right, if you just put a treatment on one person or two people, you just may have picked really crazy people with crazy characteristics. If you have 10 more people in that group, then you may average out all of that craziness, but the smaller the group size, the more impact anything that's odd is going to have in your results. All right, so you need to have an adequate number of experimental units in each group to fight that issue. So think about it this way. Would you really trust an experiment on just one subject? You know, that just raises your chances of having that subject bring a whole lot of stuff into your experiment that will not be averaged out by having other subjects. All right. The other issue is you should actually replicate your entire experiment, okay? Because experimental results can happen just due to chance. It's not really the effect that you think that your explanatory variable or what you impose into the thing is going to create. It could just be due to dumb luck, right? So if you do this experiment over and over and you see the same result, then you can kind of cast out the chance outcomes in favor of, yeah, I think I'm seeing an effect in this experiment. All right, so here is the rat example, okay? So let me just kind of highlight what's happening here. You're starting this out with 30 rats, and they're going to all be male, so there's no gender effect. They'll all be white rats, so there'll be no breeding effect, and they're all going to be newly weaned, which means they're very young, and so they're all roughly the same age, so there will be no age effect. Okay, otherwise, they will live in the same environment, under the same conditions, with the same kind of daily routines. So you're making everything as even as possible. Okay, so you're going to randomly pick 15 for groups. That's your random allocation. Now, if you don't like the word allocation, just use assignment. It means the same thing. So take the cage number 0, 1 to 30, put them in a hat, pick the first 15, they go into group 1 because you've randomly picked a simple random sample of 15. Now, do you need to randomly assign the other 15 to group 2, or are they just already randomly picked? Because really, if you randomly picked 15 rats for group 1, you randomly didn't pick the other 15 for group 1, so they are still random. Dump them into group 2. All right, so now you're good. Each group gets a treatment. Say what it is, right? You're trying to communicate what you're doing, so don't just put treatment 1 without knowing what that treatment is. Treatment 2, and at the end, you're going to compare average weight gain, right? Don't write that you're going to compare results, because results could be anything. They could be weight gain, they could be a gain in the length of the animal, they could be a gain in the lifespan of the animal. Could be all sorts of things. So if you don't say what it is you're comparing, no one is ever going to know. Okay? All right, so then 2 questions for you. Is it okay? I mean, this is actually very easy. It's very quick, and it just goes together really quite well. Just get all the parts right. But could you do this same thing in a paragraph form? And the answer is sure, why not? So if you opt out of this and opt into a paragraph form, I am ready to grade either one. Some experimental designs are actually easier to write in paragraph form. It's just whatever you want is fine. The other question is, remember the organizer we learned on Friday? Can that replace what you're looking at here for a completely randomized experiment? And the answer is no. That's a good organizer to help you figure out factors, treatments, levels, all that kind of stuff. Interaction of 2 factors or the level of 2 factors, but really, here's what you're starting with, here's what you're ending with. A lot of that information just is not present. So don't put that organizer up here when you're asked to, diagram or to write out an experiment. So that is a completely randomized experimental design. See how easy it is? Nothing to it. So what you're seeing there is that all experimental units are assigned or allocated at random among the treatments, and they produce groups which are similar in all aspects before the treatments are applied. So you've got some great control going on. Comparative design ensures that influence other than diets operate equally on both groups. They sure do. That's the randomization. Thus, the differences in average weight gain must be due to either the diets or due to random chance. Now, we want it to be due to the diets, but it could be that you're seeing something that's just due to chance. And yeah, you can replicate to see if you get the same result, but let's move on to another item of interest that we can apply just to this idea of random chance. And that is statistical significance. So this is one of those things like bias that we're just going to carry with us all the way to the end of the year. So get used to it. All right, before I pull up anything here, let me just, let's talk about that same experiment. With the rats, and let's just say it's supposed to run for 28 days and you run it. So on the 29th day, you take all of the rats in the old food treatment group and you weigh them and average them. And I don't know what rats weigh. Let's just say the average is 50 kilograms. Not kilograms, that's a big rat. All right, 50 grams. And let's just say that you weigh all the other ones with the new food and you get an average of 51 grams, right? So on average, they gained 1 gram more. All right, does that impress you a lot as being a big weight gain? If you're not sure, what about if that second group actually, instead of weighing 51 grams on average, weighed 60 grams on average compared to 50? All right, now are you a little more impressed? All right, that's your concept of statistical significance. While results may show a difference, and come on, there will be a difference. I mean, if that average came out exactly the same for both, that would just be a stunning miracle, all right? Results will show a difference between groups and experiments. We need to make sure the difference is statistically significant, which means that it's an observed effect that's so large that it would rarely occur just by chance. Okay? Where that actually happens depends on what you're measuring, what's your experiment is about, what you want to feel like is the tipping point between chance and an effect. That's totally up to you, but it is an issue. It's just another one. There's so much we have to take into account. All right, so statistical significance is something you have to consider. All right, hidden bias. Now we're going to shift away from animals to people because a lot of what we do in our attempt to run an experiment can ruin things, all right, with people. So unequal conditions, you know that, they produce bias. Okay, when we know what treatment is assigned to which subject, it's difficult not to let that knowledge influence our assessment of the response, even when we try to be careful, all right? Remember the placebo effect, where, some guy in a lab coat comes out with some pills and says, hey, Mildred, you're getting the good stuff today. And it doesn't really matter what Mildred gets, she's just going to feel like on top of the world. All right, that's what we're talking about. So in order to avoid the bias that might result from knowing what treatment was assigned, we're going to end up blinding, not literally, but we're going to rob those people involved in the experiment of the knowledge of what treatment goes to whom. All right, so there's a little bit of complexity to blinding, not much. There are two main classes of individuals who are involved in these experiments. There are those people that are either the subjects or directly involved with them. Think about people that bring them the medicine, or people that take their blood pressure, or people who fill out charts, or people who sweep the floors. Anybody who is in contact with them should have no knowledge of what kind of a treatment these individuals are getting. The second tier is going to be those who are evaluating the results. So they could be people who are judging them, tabulating them, treating physicians, anybody who's there after the fact looking at the numbers. And they could look at a number and say, oh, well, that was a placebo. That's way too high. I think we need to lower it. All right. I mean, you wouldn't expect people to just, change numbers like that, but who knows? You just don't want any kind of temptation there. So when all the individuals in either one or the other of these classes are blinded, when they're not told what the individuals are getting for a treatment, the experiment is said to be single-blinded. What might even be better is if neither group, the individuals in neither group, know what the subjects are being treated with. So when everyone in both classes is blinded, the experiment is called double-blind. And I just saw that on TV last night. They had, if you watch the news, there you go. They're going to just shower you with medicine commercials. And they're always talking about a randomized comparative experiment that's double-blind, blah, 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 blah. Well, now you know what double-blind means, all right? So it's an interesting thing, and yet it's another thing you have to worry about when it comes to experiments. So, yeah, not only do you have to set the things up correctly, but you have to have your 3 principles of statistical design for experimentation. That's going to be control and randomization and replication. I may have mentioned 4. Most books use these 3, but we'll throw out a possible 4th one tomorrow. All right? Then you have to worry about blinding, and you have to worry about statistical significance. And it's just a complicated thing. But if you can get things tuned just right, then things will be gold. And you can have knowledge that you will include into the sum total of human knowledge. That's a good thing.